Thank you for Michael's introduction. My name is Baolisha, and I am a PhD student from Stony Brook University, advised by Dr. Barbara Chapman. As you can see, this work is collaborated with Total Energy and Lawrence Gilmore. So as its name, the title is about discussion of blah, blah, blah. So this is not a from the beginning to the end framework or a very complete framework. So this is just a discussion about what if we want to have some device-to-device or collective communication inside OpenMP target offloading? An interesting fact is the second presentation is about OMP core to also implement a more complete collective communication library. So, but we also implement some collective communication. I'll introduce later. So let's begin. The background of this work is really simple, is that we have more and more supercomputer with multiple GPUs in a single node. For example, Pure Motor has 4 GPUs, and one Summit node has 6 GPUs. But as you may also know that for AMD GPUs or Intel GPUs, one physical GPUs may have multiple logical GPUs, such as Frontier. They use MI250X, and one physical GPU has 2 logical GPUs, which is called GCD. And in Aurora, the Intel GPUs, they have the tiles, which means that we have more and more devices in a single node. So we want to some support inside OpenMP could have some device-to-device integration. Currently, we have some in OpenMP current spec, we have some directive or runtime library routines, such as you could assign your directive to a specific device or to call a specific function, such as OMP get mapped pointer. You could get the device pointer from a specific device. But if you want to do some integration between devices, what you could do. In current spec, we have 4 APIs, actually only one, because all of them are about target memory copy, which means that you could copy some memory from the GPU device, from the device memory to the other device, or from the host device. But definitely you may know that if we want to more integration between devices. So here is a screenshot from the Brownies in SC23. Actually, I saw this slide multiple times. I remember last year in Michael's presentation, we have the same stuff about the OpenMP spec beyond 6.0. You can see they want to have some support for using multiple devices, such as automatic operation, such as bulk launch, such as broadcast, multicast, or some other supports. And inside of these sports, we could have 2 types. The first one is communication, such as location, broadcast, multicast. And we may also have some communication, such as bulk launch, work distribution, let's say target region. And this work, we mainly talk about the communication stuff. So the first one we want to discuss is about the topology. So the left figure shows the topology of a pure motor node. You can see we have 4 NVIDIA A100 nodes, and the right figure is a Frontier. We have 8 logic AMD GPUs, and the topology is really complex. The left one is simpler because every GPU, the topology of GPUs are symmetric, but in the Frontier, it's totally asymmetric. Let's take a deep look. I put a compass here to make sure that you will not get lost. There are some texts I got from the Frontiers for Computer paper. They said the nodes also use a group of 1, 2, and 4 XGMI 3.0 links running at 50 plus 50 gigabytes per second. Connect 8 GCDs I introduced. You could see here we have 8 GCDs. We have 1, 2, or 4 links. And they say, oh, if the 2 GCD are in the same physical GPU, they use 4 XGMI link. If they are in the north or source, they have 2. And if they are in the left, or the east or west, they have only 1. Such kind of asymmetric brings up a biggest problem is we could see a bandwidth matrix here. This is totally asymmetric bandwidth. Because if you want to transfer some data from the GPU 0 to GPU 1, it's fast. to GPU 6 or 7 here, it's not so that fast. But if you want to transfer data from the GPU 0 to 2, 3, 4, 5, it's really slow. The thing is, if we want to have a very good performance, you need to think about how could we mapping the devices. We should know the topology of the devices. That's very important. So let's come to our first question. How can device topology be abstract and exposed within OpenMP to support efficient and portable design of device-side collective communication or collective operation? So the motivation here is GPU interconnect bandwidth and latency vary across different link, maybe from different types such as NVLink, Infinity Fabric, XE-Link, PCIe, or maybe they use the same link, but because as I just show you, maybe different number of link. So we want to propose some new APIs for OpenMP to show that the topology inside the nodes. So here is the new APIs we propose, which records OpenMP device link type. Definitely, this is just some API we propose. So definitely, if we in the future we have it in OpenMP spec, it will be not look like that. But let's take a look. So we have different types of link, such as NVLink, XE-Link, different bandwidths at GMI, the AMD link, or PCIe, or something you don't know. And we also have the get device link type so that you can know that if you want to have a higher bandwidth, you want to know that, oh, I want to just transfer some data from one GPU to the other GPU, or we want to do some hello exchange, which will be more complex. You may also want to get a device bandwidth matrix. And besides topology, another question is about group. If you are familiar with MPI or any other SPMD mode, such as OpenSwarm, you must be familiar with such kind of concept. In GASM, it's called group. It's called group or team. In MPI, it's called communicator, which means that you don't always want to do some collective communication among all the devices you have. So you want to set up a group. You just want to control to do some operation among a subset of GPUs. So a device group is logical set of GPUs that share a communication context. So we propose some new APIs to create, use, and free a GPU, or I should say device group, through a lightweight runtime inference. Here it is. So we define the OMP device group, and we also provide two functions, which is called OMP create device group and free device group. By calling such kind of stuff, you could do some collective communication within a group rather than call the operation among all the devices you have. The next one is allocation. This is just a tricky point because the scenario is a little bit restricted. The scenario here is you want to map in some data which is identical, which means that the size, the content you want to map in is the same. Why do we want to propose this idea is because we find in current supercomputer nodes, in current cluster, the GPU to GPU bandwidth is much higher than the CPU to GPU bandwidth. Definitely, if you use APU or use Grid Super, you could just skip this part. But if you use you are not using the Grid Super chip, or you're not using the APUs, the CPU and GPU have their own memory, you should think about this because GPU to GPU bandwidth, such as NVLink and XGMI, have a higher bandwidth compared to the CPU to GPU bandwidth. So the idea here is you want to map some data from the host device. The better idea is to do one mapping and then to broadcast because you could use a higher bandwidth between GPUs. And next part is communication. As I just mentioned at the first beginning, we implement some collective communication, but we just implement broadcast. We use two kind of algorithms. The first one records First one is records the topology of via ring broadcast. The second one is pipeline binary tree broadcast. Actually, this two algorithm is used in the X core, such as N core or R core, even in maybe MPI. I'm not sure. I didn't take a look of the MPI source code, but both of them I use point-to-point data transfer. we directly use the GPU to GPU higher bandwidth, and we will slice a message, especially you transfer large size of data. We will slice a message from the large size to a smaller size. And the last one is asynchronous process, because that's it, what collective communication should do. And we did our evaluation on 3 platforms. The first one is located in Lawrence Livermore, but it has the same topology as I just mentioned with Frontier. The second one is Pure Motor, which has 4 NVIDIA A100 GPUs, and the third one is Aurora. You may say Aurora also has 12 logic GPUs, but actually by default, it seems that it has 6 Intel GPUs, so we just use 6 GPUs here. The first one is topology. As I mentioned, that the Frontier has a asymmetric GPU topology. So if you want to transfer some data, such as you want to do such kind of chain hello from the 0 to the end, if you use the default mapping, you transfer data from 0 to 1, 1 to 1 to 2, 2 to 3, something like that, you will find the link between different devices is not the highest. On the contrary, we could use the optimal solution, which is we will fully utilize the higher bandwidth between the devices. With the optimal mapping strategy, we could have a very good improvement. For example, we have at most 23% improvement. And when the size of data transfer is larger than 8 megabytes, the average speed up is about 19%. And actually, we also trying to do another work is we want to make a framework to have the optimal mapping automatically rather than you write it by hand. The second one is allocation, as I just mentioned. Why use one mapping plus broadcast rather than mapping multiple times? You could see, especially you transfer large size of data, you will have a better performance, whether in AMD or NVIDIA GPUs or in Intel data center GPU. The next one is broadcast. We implement some broadcast algorithm. You could see in some scenarios, especially in NVIDIA, we have some. In some scenario, we are good than the NIC core, and in some scenario, we are good than R core. And I'm not very sure what happens in Intel data center GPU, because in all scenarios, we are better than 1 core. But one thing I want to mention here is not like NIC or R core. If you want to launch a program with 1 core, you have to core MPI, which means that you will have 6 MPI process here, but we just have 1 process for the OpenMP broadcast operation. So I don't think this is a fair game, but to make it complete, we put the Intel data center GPU data here. So it's concluded. I think my presentation is a little bit too short. So we discussed the impact of device topology, which is very important, especially for some mapping strategy. And we propose some new APIs for topology and group APIs, which is very important for collective communication, especially if you have experience in using MPI, you may know that what I'm talking about. And the next one is we propose some tricky point about mapping and broadcast. If you want to mapping identical data in multiple devices, no. The last one is we implement some two broadcast algorithm, and we have a not bad performance. Because my next presentation will have I believe they will have a much better performance in any other operations such as reduce or reduce or alter or. That's all my presentation. Please let me know if you have any question.
All right. Good. Questions?
I got confused there. Going back to your graphs, what was being mapped to what? There's some of those.
Yeah, you mean? Yeah, this one.
What's going on here?
It's like you have, assuming that you have 8 AMD GPUs, you want to map, for example, you want to map 100 megabytes data to all of these GPUs. But what we usually do is we do 8 times mapping from the host device. But what we do here is we just map the data from, for example, we just map data from the host to 1 GPU. and then do one broadcast operation. The broadcast
So
operation,
you do a mapping from the host to one GPU.
yeah,
And then you broadcast from there.
yes,
To the other GPU.
yes.
Thank you.
Is this, thank you for the talk. Is it the same thing you are doing for the Intel GPU?
Yes, it is.
On Intel GPU, the X-Link, it's very slow. If you use single X-Link, it's like 15 gigabytes per second, while the PCI is 50 gigabytes. So
Mhm.
this strategy on this architecture is probably not the best heuristic. You probably just want to use a PCI, which is faster, because there is one PCI per GPU.
I see.
Another thing I know there is not for MJCH now, but people are doing MJCH running on Aurora. I think they are splitting. So these X-Link are quite slow, but there is many between every GPUs. So they are when a GPU is want to communicate with another, they will split the communication between different links to sort of use the maximum flow possible. So these are the kind of things that are being done on the Intel GPUs.
Okay. Because compared to I will admit that as a compared to the AMD GPU or NVIDIA GPUs, we did less experiment on Intel GPUs because we could write, for example, we could write we write some CUDA code for NVIDIA and we write some heap code for AMD, or we use, but the only thing we could use for Intel is we use OpenMP target memory copy. We don't, at least for myself, I don't know how to write good performance SQL code. I have to admit that.
So I'm not sure, maybe I'm missing something, but you're doing a broadcast and it's or different collectives, but they're initiated from the CPU, right? So if you, for example, want to do a broadcast and if the data is actually laid out in such a way that you have multiple connections to the different chiplets, why don't you just split it up in 4 ways and send it to different GPUs and then perform the broadcast internally, which has much higher bandwidth? Have you considered that? Do you know what I mean?
Not really.
Because I mean, the problem is basically you need to move the data over from DRAM to the HBM.
Yes.
But the HBM is broken up into different pieces. It acts as a NUMA as well.
Yes.
So if both the CPU and the GPU act as a NUMA with different links,
Yes.
then you can use these links in parallel to break up, say, 1/4 of my broadcast. And if it's already distributed that way,
yeah, that's
you
a
get
fair.
much better bandwidth.
Yeah, I think that's.
You should look into it.
Yeah, I think that's a very good point. I think that we should propose some new APIs for OpenMP.
Well, I mean, can't you hide that? The main point with this one is if you want to use it, you need to find a way to distribute the data in memory over the node so that it is suited for this kind of paradigm. So you need memory management on the OpenMP side. That would be the interesting part.
Yeah, I think last year we have the paper about the topology between the CPU and GPU. I think there's something similar or.
Okay, are there more questions? No, I have one.
Okay.
So in the paper you had, and on your slides, like different kinds of links like NVLink, XPMI, and so forth. How much do you actually care about the link versus the property or the traits of the link, like high bandwidth, low latency, whether it's NVIDIA link or AMD Infinity Fabric, probably doesn't matter, right?
Yeah, I think that's maybe if we really put something into the spec, I think that should be some low latency, low bandwidth, high bandwidth, rather than this is a little bit meaningless. We put some different vendors name here. Yeah, I think that's true.
All right, okay. One last, yeah.
So do you need a user to provide that information about the topology or putting the programming like, oh, I need to dictate that your code should be, I mean, the way of broadcasting or the way of communicating should go through this route, this route.
In our,
I mean, your API, whether your API requires for providing the mechanical user to specify how they want data to be broadcast or moved.
You mean for this one or
for your API?
I think it's highly dependent on the implementation. For example, if you want to have the topology information, maybe the thing is, just take the frontier example. We got such a matrix bandwidth matrix, but actually you cannot get it from current ROCm API. The only thing you could get as a matrix is you ran a mini bandwidth benchmark here.
Yeah.
You want to get such a bandwidth, I think the only thing is you may call a function, and the function is like it will run a benchmark and it will get some result, and then you will get the topology matrix, and then you could use this information to, do some mapping or adding some strategy here. The thing is, I honestly, I don't know why in AMD GPUs, the raw code doesn't give us enough information to get such a such a information, or if maybe we could just simply call ROCm function and we got similar stuff, and then you could have something like that. And another research we are currently doing is we were trying to write a framework like you just write and it will generate a script, and this script will guide you to have a such we call optimal mapping or optimal scheduling. That's what we are doing here.
I have one short question. When we did a similar forecast experiment with OpenMP, and one thing that we considered, we think that would be a problem besides the matrix, we also get a bandwidth matrix to get a general idea of the speed of the links, but we still have the topology problem because when you fully utilize one of those links, you're going to get contention on the others. So there's that additional topology information that is hard to get.
Yes.
And do you think of trying to get it somehow? Because that's something that we thought about for a while, but it's pretty hard, and especially if you want to be portable, like how do you consistently get this topology information, like which link saturates the other connection? So
as far as I know, I'm not sure our core implementation, at least in Nico implementation, when you do the Nico initialization, they will transfer some data and do such kind of macro benchmark to detect the topology. As far as I know, that's the Nico implementation. But Nico is they do internal, but for both internal. I'm not sure what they have really done for the internal, but I think when you do some implementation, they will try to run a macro benchmark and get such kind of topology information. So maybe if we want to implement some similar stuff in OpenMP, we still need to get, definitely, if we could get some information from the vendor API, that's pretty good. But if we cannot, maybe we should still, run a macro benchmark and get information. I think that's maybe necessary if we want to really get the optimal performance, such as what we have done for this scenario.